All right, well, welcome everybody. Welcome to the inaugural Dean's Invited Speaker series lecture for this year. We began this series last year as a way to kind of build a bridge between our alumni in engineering and an important industry leadership role, so sort of our interest in building connections to industry with our alums. It's been a great series. We've sort of generated a lot of great conversation between you folks and these alums who are eager to reconnect and learn more about what you're doing here. So my name is Jeff Brock. In case any of you don't know, I'm the Dean of the School of Engineering and Applied Science. We'd like for this to be something that's really thought of as open to the broad engineering community. So please, for future events, tell your friends, and let's get a broad base of engineering interest here. So I'm really excited today to have one of our kind of stalwart class of PhDs from 1995. We've made a bunch of great connections to this class, actually. Pushkar Tandon, who's here to talk to us about his work at Corning. And we're going to basically, the way this is going to work is he's going to give a presentation about some of the exciting things going on there. And then we'll open it up for questions afterward. So to say a little bit more about Pushkar's background, he's a corporate fellow at Corning in upstate New York. For those not familiar with Corning, it is a global leader that specializes in using material science to create purposeful technologies for a wide range of sectors. This is from the life sciences to optical communications, of course, to damage-resistant glass like on your iPhones, and to automotive markets, which I learned more about earlier today at lunch. Pushkar is an innovator himself. He's a co-inventor of clear curve optical fiber, a bendable optical fiber that is capable of bending without signal loss. He has well over 225 US patents. I look forward to learning more about what he's been up to, and I'll give the floor to him for his presentation. Thank you for joining us, sir.
Thank you. Thank you, Dean. Thank you, Dean Brock. Thank you for the kind words. You can hear me okay in the back, right? Good afternoon, everyone. I'll be talking about optical fiber and connectivity technologies for next generation telecommunication systems. As Dean Brock said, I'm currently a corporate fellow at Corning Incorporated. But before I go into my talk, I want to talk about my Yale years. Absolutely fondly remember them. Great years there. Got my PhD in chemical engineering under Professor Dan Rosner. The thesis title was Transport Theories for Particles Generated in Combustion Environments. On the left-hand side, I'm showing the day I defended my PhD, giving a copy of my PhD thesis to Professor Rosner. On the right side is formally when the PhD degree was conferred on me. I stuck around for a little bit more, close to a year, late part of 95 and early part of 96 as a postdoc in Dan's lab, but did not lose my connection with Yale. Was back on the campus. One, you would remember this photograph. This is right at Philopis around the corner. This is 2016. Have an interesting story to tell for this 2017. Both these pictures were taken on the same day. My older son, he was a rising senior in high school at that time, was taking a summer course at Yale, right at Silliman College here. So you can see the Silliman College in the background. And I had come to drop him and decided I'll link up with Dan, and we decided to have a brunch at Atticus, and we talked for about 2 hours. Those 2 hours resulted in 4 papers being published in Aerosol Science and Technology in subsequent years. That's the most productive 2 hours I've had ever. So this photograph is right out at Atticus. Career since Yale, since leaving Yale, 97, 98, I was a postdoctoral fellow at Institute of Medicine and Engineering and Chemical Engineering at University of Pennsylvania. and worked on cell aggregation, neutrophils and platelets. How do they interact and how do they aggregate in blood flows? Since '98, I have been with Corning Incorporated working on optical fiber cables, optical fiber connectors, diesel particulate filters and substrates in vehicle after treatment systems to get rid of the noxious fumes or the soot particles that come out of the engine. Worked on specialty glasses for UV and EUV lithography, and glasses for consumer electronics, including the glass on our computers that we carry in our pocket all the time. Inventor on over 230 US patents and 350 patents worldwide, additional 50 to 75 patents pending with the US Patent Office. Author on 70 peer-reviewed publications and 50 conference presentations, and some of the select recognitions include being inducted in the National Inventors Hall of Fame, multiple awards from the American Chemical Society. One of the inventions also noted for Time Magazine's Best Invention of the Year, and currently also act as an associate editor with the Journal of American Ceramic Society. Talk a little bit about Corning. It's been around a while. It was incorporated in 1851, moved to upstate New York in 1868, where it still is. Its headquarters is in Corning, New York, not very far from Cornell. And it has about 50,000 employees worldwide. Last year, the core sales were $13.6 billion. But we do put in about $1 billion back in RD&E. So that's about 8%. Not many companies do that. So that's a lot of, so innovation is at the heart of what we do, and we are one of the leading innovators in material science. Very long track record of life-changing innovations dating back 150 years. Made the first lenses for the railroad signals when they came into being. Made the glass bulb for Edison's glass bulb. For a while, there was a ribbon machine that helped in electrifying the electrification of the world that was coming out of 7 or 8 ribbon machines that existed at that time. A few other ones: television picture tube, telescope mirrors, windows for the space shuttle, low-loss fiber, and we'll talk a lot more about it today, catalytic converters, particulate filters, among others. I won't go into all the detail, but some of these ones over the last 150 years. Industry leader in these 5 market access platforms, but it's the LCD displays that we have on televisions, on monitors, mobile consumer electronics. I already talked about the one on the Gorilla Glass on the phone, but also things like stepper lenses for lithography. The glasses need very high precision. We make that. Optical communication, we will talk a lot more about it. Automotive, I talked about, but also in life sciences and pharma. My talk today will focus on optical communication. And to start with, I will say we invented the first low-loss fiber back in 1970. So it's been a while. We invented it in 1970, but it did not get used in a commercial telecom system until 1982. So required about 12 years of very patient investment when there was no business case available. So we continued to plow money in there. But since then, 82, it was put in the first system, telecom system. Since then, over 1.5 billion kilometers of Corning-made fiber has been installed all around the world. Here, what I'm showing is the original patent from 1972, and 3 gentlemen, Keck, Maurer, and Schultz, who were the inventors of low-loss fiber. It has been installed over 1.5 billion kilometers, and today, at the rate at which we are installing fiber, it's equivalent to going around the circumference of the Earth 20 to 30 times a day. That's the amount of fiber that is going in every day. And what is driving it? There are secular trends that is resulting in that very robust growth in internet traffic growth. And if you look at, it's not only here in US, across the world, the annual growth rate is about 20% all over the world. Because most of the governments, including the US government, they are investing in connecting their communities with high speed. There's a program in US that is called BEAD, Broadband Equity and Access Program that is there. And the US government is funding to the tune of $42 billion to get that communities to not only the urban communities, but also the rural communities as well. So that secular trend is there. AI is another one that we hear on everyday basis. That's another one. So all of these trends are the reason why we are seeing the very steep growth and why more and more fiber is getting deployed. One of the things that we have seen through our own techno-economic analysis is if you were to plot a data rate on the y-axis and the distance over which that data rate is plotted on the x-axis, the product of these two numbers, when it starts approaching about 100 gigabits per second times meters, that is where the techno-economics actually, so it's not that connectivity wasn't there even 100 years back. It used to happen. Telegraph used to happen over copper cables. It used to be there. But when the data rates and distance, it starts hitting that kind of a magic number of about 100 gigabits per second times meter, that is where the techno-economics starts favoring transition from copper into glass fibers, which you can transmit a lot more data on glass fibers compared to on copper. So some of the technology vectors which describe our next generation of product development, here are 4 of them. Scalability is how do you scale it to connect more and more people? How do you scale for a particular application? How do you scale to larger? That's one thing that we focus on. Second part is, in the same space, how do we have higher density of connections? And some of these will become a little bit more clear as I talk about some specific application. Third one is ease of deployment, how easy it is to deploy. And fourth, which is becoming more and more important, that is sustainability. And I know this is the generation that care a lot about sustainability. So I will focus on 3 important use cases and try to, the 4 vectors that I showed, how they blend in, they have been demonstrated with help of 3 use cases. The first one is optical connectivity in hyperscale data centers with artificial intelligence clusters. And one of the reasons why I picked this particular topic, I was actually enthused by this announcement that was made at Yale a few weeks back that had to deal with Yale announces the commitment of $150 million in investment for AI leadership. And that was one of the reasons I picked this topic to talk today. So if you talk about hyperscale data centers, these are data centers. This is not the university data centers, which are small in a small building. These are huge. Can involve multiple buildings, can be the area would be greater than 1 million square feet, and a whole bunch of servers which are connected to the switches. They will be part of the data center. And you can see over last 8 to 9 years, the number of data centers, they have almost tripled. These hyperscale data centers, they have almost tripled. So connecting all these servers to the switches, it's all done through optical links. It already is a challenging problem. But when you start on top of it talk about now, let's make these scale data centers to be compatible with AI, it becomes even more challenging. Why does it become challenging? There is your front end. There is your front end network, which is connecting your spine, leaf, and rack switch to all the servers. But then there is a back-end AI that is working on the front-end network. And when that happens, the number of optical connections can increase almost by an order of magnitude. It can increase by 10x. And because each of the GPUs needs to be connected to the other GPU that's over there. So connections can go 10x. And then what you can land up with, one of the switching racks can have, which may not be maybe of something smaller than this, it will have 10,000 connections. Think about 10,000 optical fiber connections that you're making in such a space. When you do that, it creates a massive fiber routing and management challenge. And when on the previous slide, these servers look very clean. Here, when you see those connections, all those optical fiber links that are being connected, it's messy. It's very messy. To get to that level of congestion, what has been proposed is you are trying to make your cable smaller with the same number of fibers in there. You are making your fiber smaller, you are making cable smaller, and you are making your connectors smaller. When you have a smaller cable with the load that, these are intertwined, all these things, they experience a load. The load makes these cables to bend a lot more. When it bends a lot more, there's a loss associated with it. And what that loss does is, it increases the link loss that you have from one end to the other. And if that link loss is greater than the budget you have had for the link loss budget that is acceptable, that link will fail. So some of those links will not work. They call it a phenomena called flapping inside the data center lingo. That is exactly, they will fail, and it causes issues. The main impact of the issues, this is some of the statements that have been made in publications from main hyperscale data centers. A 0.1% loss in packet loss can drop the throughput by 25%. So very disproportionate impact. The number of links failing might be small, but the impact is huge. Similarly, another report says for video traffic application, loss rate of 0.01, they have to reroute the traffic because the link is not working. It causes a drop of 50%. And sporadic losses can cause virtual machine reboots, not very good for the network. So I did talk about if your link loss increases the link loss budget, your link will fail. There are multiple mechanisms that contribute to the overall link budget. And these can include, you have higher attenuation, lateral offset, you have two fibers coming and they are getting connected at a patch panel. If they are off by more than a micron when two fibers are coming at the connector space, it will cause an increase in loss. It has to be that precise. If there is an air gap at the patch panel where the two fiber and two connectors are coming, that will cause to a loss. Bending, I already mentioned, there is increased load, cables can get bent, fibers can get bent as a result. And if there is contamination, dust, if it's on the face of it, all of these contribute to that overall loss that you have in a link. And what we have done at our end to mitigate this problem is to do the congestion problem, address the congestion problem. We have a new fiber. Dean Brock mentioned clear curve. That was a bend insensitive fiber. I say contour as a clear curve on steroids. It's much more capable. While back compatible with the legacy fiber and has bend-in sensitivity. You can bend it to very tight bends and will show no loss. We have taken these fibers and put it in cables where these cables are smaller, and we have packed in more number of fibers in there. And we have also developed connectors where the density can be increased almost 36 times. So all these things help in managing that congestion that we have. If you were to do overall link budget in a typical deployment scenario, you will see in the peach curve that is with a fiber that is being used today. The blue one is the one where you will, that is with contour, and you can clearly see that contour being much less bend sensitive, you can drop it quite a bit. You can drop the loss quite a bit. Here's the Monte Carlo scenario of different kind of deployment scenarios that you may have. And this Monte Carlo analysis is saying, currently the fiber that you use, you will have a loss distribution. Most of it will be fine. Most of your links would be fine. But there is that long tail that may account for about 1% of the loss. That would be there. But if you use the contour, you will have no percentage that will approach the link budget. Now, somebody will think, why do you care about 1%? When you have that many links, that 1% can be thousands of links that may be failing. It's a big deal. You heard me a few slides back saying small percentage having a disproportionate effect on the overall network. 1% is a pretty big deal. So contour is your insurance policy. Whatever, you may abuse the fiber as it is getting installed. You don't need the skilled labor to make it work precisely. That's the insurance policy that you bring. The second use case I would use is increasing the transmission capacity in submarine cables. And why are submarine cables important? This is kind of a map, 23 map. I pulled it up from Google. That represents the 606 submarine cables that exist in the world. Why are they important? Because 90% of all internet traffic goes over some kind of a submarine cable. These are cables that are connecting continents. And installing submarine cables can be extremely expensive. It can be anywhere from $30,000 to $50,000 per kilometer. And a transatlantic cable connecting East Coast to Western Europe, that project can be on the order of $300 million. So it's pretty expensive. And how these cables are there, these fibers are there, and they are protected by steel wires and polymers. And the way you install it is, these ships would go, these are the cable tanks which have these cables. And it's almost like plowing a field. It creates the area, and then you install the cable over there. This is a real one of the cable tanks that is there. That cable is getting installed. And it will get installed on the seabed. But think about, if you are terrestrial application, you are doing it on land, you can put an electronic hut and regenerate the system wherever it is needed. Not easy to do it in an ocean. So you need to have absolutely very low loss so that you can go much further distance. A typical loss for a submarine cable is somewhere like 25% lower than what is used for terrestrial cable. And fighting for loss, which is even 0.001, that's the third significant space in dBs per kilometer, it's a very big deal. You have to jump through hoops to make it happen. Getting 25% loss, it's a pretty big deal. So I will show this plot is from Steve Grubb, who used to be at Meta. What is called, it's an equivalent of Moore's law, it's the Neptune's law for how the submarine capacity is increasing. Prior to 1988, 1988 was the first year an optical fiber cable was put under the sea. That was called TAT-8. All the TAT 1 to 7, they were copper-based system. And you can see the capacity has increased quite dramatically. This is a log scale over last 35 years. We are currently at close to about half a petabyte. That's about 500 terabyte. And but we are at the limit by putting in the maximum number of fiber pairs that we can put in the cable to reach that capacity. Unless we increase the size of the cable, we cannot add more fibers. We are getting to the limit. But are we going to stay here, or this line, the demand will keep going up? So you need new technologies to make it happen. If you cannot put more fibers if you make your cables bigger, it adds to the drag on the seabed. It adds to the weight that can go onto the ship. All of those things adversely affect the installation. So you need a new technology. So I will put here a law that is attributed to Claude Shannon, the father of information theory. He got a Nobel Prize for this as well. How you can increase the cable capacity. So you can improve your transmission system to improve signal to noise ratio, but that term is inside a log. You will have to change this by orders of magnitude to have an effect of factor of 2. But other ways is you can do is, there's another way. Currently the transmission happens in the C-band. That's a range of wavelengths over which transmission is done. You can go to other bands, but the efficiency is not the same in other bands, so it's not easy to scale. Or you can increase the number of paths. One way to increase the number of paths is have more fibers, but obviously that is not compatible with increasing the size of the cable. So question to ask is, can you put in more cores in a fiber? That is the way that is being explored. We were talking about multi-core fibers today morning. That's what it is. So if you look at it, traditional fibers, light goes in, light comes out, it's a single core. You put more than one cores, yeah, you can do it, but it's not, there are technical challenges that need to be overcome. First and foremost, if you put the two cores together, there is a coupling between the two cores, and there is a crosstalk between them. Signal you may launch into one of the cores, it will start appearing in the second core. And if you say, okay, I will put them apart such that there is not enough crosstalk, there is not enough coupling. If you put it too close to the edge, light can get tunneled out. There is a radiation loss because the coating that you could put on the fiber has a higher index. Most of the coatings are higher index, so light gets tunneled out. So it really becomes an optimization problem. We are trying to manage the coupling between the cores as well as the amount of the light that is coupling out. And if the crosstalk is above a certain value, you would see that you'll start taking an SNR hit. Going back to Claude Shannon's formula, you'll take a hit on the capacity as well. So as I said, you have to design your fiber and your core such that you are doing a balancing act between the crosstalk between the cores and the loss that can happen by leaking to the outside of the periphery. And we took all that, did the physics. This is a cross-section of a real-made fiber, and we were able to measure the crosstalk on a system which was below that limit where you start putting in the SNR penalty. And here are data shown for attenuation, so that tunneling loss starts showing up in the transmission loss. The crosstalk is shown over here. And based on our theoretical work as well as experimental work, this was the right intercore distance that would work. And we demonstrated the loss on this fiber, which actually was a world record. This is right out of a recent publication in Journal of Light Waves Technology. We demonstrated, yeah, this is a record attenuation loss and a drop-in replacement for a single core fiber. For the customer end, they can take a single core fiber out, put the multi-core fiber. It meets all the attributes. It's a drop-in replacement. That's a big deal for them. Third one, and I don't know how I'm doing on time, but we'll try to go over quickly, is I will talk about a solution that we bring to our hyperscale data center customers, which has value for them, but it also has an implication for environmental, the sustainability aspect of it. That is becoming more and more important. Why the use case I'm going to talk about is, I showed you one of the pictures of the data centers which has multiple buildings. There are servers sitting in one building, there are switches sitting in another building or servers in another building. They have to be connected. How do you connect that? You connect it through optical fiber. So these are two buildings. They are connected through optical fiber. And there can be many connections. I'm doing a use case for our customer. Say there are 30,368 fibers that need to be connected between these two buildings. Yeah, you can get the cable to be connected between the two buildings. But when it arrives in one building, what do we do with this cable? It still needs to be terminated and connected to an equipment. If you are doing splicing, if anybody has an experience with splicing, it's painful. If they have to do connecting 10,000 fibers, what will it take? Even if you are doing multi-fiber splices at one time, 12 at a time, 8 minutes per splice, $40 per splice, it will take 115 hours. And it will cost $35,000. But this dollar value pales in comparison. It takes that much time for it to be done. So for that much time, that data center is not getting used. That is even more important. So one is, and the other part is, to do all this, you need skilled labor. You cannot get somebody off the street and do that. You need skilled labor to do that. How do we solve that problem for our customers? What we say is, we will put connectors at the end of the cable, and we will provide you with a solution which you can get your data center operational faster, which minimizes the risk because we would have tested these connectors at our factories. It will have lower carbon footprint, and you do not need to be the amount of conduits that you need to connect the two buildings, that gets reduced as well. That's the value we are giving. What does that solution look like? That solution looks like is currently, I think I mentioned somewhere, currently the way it is done is, if you, to get these things, you use 144 fiber cables and use a lot of them. But what we are suggesting is, so this is legacy solution, 144 fiber. We are suggesting highly dense cables with a lot more fibers there, and you actually need just 3 of these. Each of these cables are 3,456 fibers. And to do, and it's not that, yeah, what's the big deal? You are making a smaller cable, packing more. That's not it. There are a lot of technical challenges. These cables are sitting out there. They have to behave just like what your legacy solution would look like. So it has to meet all the requirements. There are a lot of technical challenges that need to be solved. And by going to a single cable with high fiber counts, we reduce the jacket material by 70% and weight by 60%. That does show up in the carbon footprint you calculate for the solution, and I'll talk about that. Then what we do, so with this high density cable is there, we terminate it with connectors. And these are standard connectors, maybe 24 fibers in each connector. And then this is another fascinating part. You take this assembly and you put a pulling grip on top of it, and you can actually, using air, traditional method of installation was you will pull cables over distances. Something which is becoming more fashionable these days, you are using air to actually propel these cables. They become low in weight that you can propel it, and you can go 1.5 kilometers to 2 kilometers using air as the medium. That itself is actually a very good, and these routes are not always straight. They have bends and stuff like that. And so you use air blowing or jetting as a method to install these cables. It arrives in the other end. You can take the pulling grip off, open this up. These connectors are already there. You don't need the skilled labor. You put the connectors in the patch panel, and it's ready to go. The hard work has been done in our factories so that it becomes easier for our customers. So if you are connecting these two data centers using this cable I just mentioned with the fiber and the connectors right over here, what does the solution look like? This is on the leaf switch end. You will have a 5-rack unit. You will connect this cable across buildings. It will arrive on the other end. There is a patch enclosure. These connectors can be connected. On the back end, you can connect with these trunks, connect it to the unit. You can get your data center working much more faster. So our job, if you look at it, we are not running the large language models or servers or anything. Our job is glorified plumbers. We are but key enablers for all these things to happen. A traditional solution would look many cables, 320 of them when you were using 144 fiber. This one single, you only need 16 of them, a lot easier to implement. Now let's talk about the environmental impact. So sustainability is becoming increasingly important for our customers as well as for us. And we do life cycle assessment for a lot of our products. This is doing what is the scope 1, scope 2, scope 3 carbon footprint contribution that is coming for our products. Some of them are cradle to gate, some of them are cradle to grave. And what we did was use this approach to find the carbon footprint of the new solution, compare it to the legacy solution. So first you look at just the optical fiber. Turns out its carbon footprint per kilometer is about 2.3 kilograms CO2, but almost 70 to 80% of that is coming because of the electricity needed to process the glass, to making the optical fiber. Only 20% is the raw material. So obviously, if you have to think forward, how do you reduce the carbon footprint of it? Make these fibers even smaller till the time you can meet the optical performance. That's one way. But the fact that 80% is coming from electricity, any renewable source of electricity will reduce the carbon footprint. When you take that fiber and take it into the cable, that represents actually the situation shifts completely differently. Here it is dominated by the raw material. Optical fiber was only 20%. In the cable world, there is so much polymer that that's the major part. The fact that we were reducing in a new solution jacket material by 70% and weight of the cable by 60%, both of those things help in reducing the carbon footprint. And as a result, when you do end-to-end assessment of the global warming potential or the carbon footprint, you can reduce the carbon footprint total almost by 25 to 30%. That's what it is. Some of these things captured in this IWCS paper from 2022, and this is a white paper that I have authored, how connectivity with optical fiber, it's a much more sustainable solution. It anyway is much more sustainable, but on bit basis, it's sustainable by 3 or 4 orders of magnitude. So I will close my talk with this slide, which has to do with how Corning engages with universities at different levels. We have a lot of sponsored research, service agreements, material transfer agreements, measurements that can be done here or at Corning, and but also we view our collaborations with universities as providing the next generation of our employees. Good employees and good scientists, that's what we look for. And from the other research agreements part of it, any opportunities to collaborate, I look forward to that. Thank you. We'll be happy to take any questions.
Okay, thank you very much, Pushkar. We're not going to feed back against one another. So I had a question to start out, which is you talked about the role of optical fiber and optical transmissions in AI and in data centers. Are you using AI to do materials design for the development of novel materials and new ceramics?
It's almost inevitable not to jump on the bandwagon. The hype is immense. But how do we effectively use AI? We are trying to figure that part out. There is some things which have started to happen, but is it a well-defined part of the innovation process? We are not there yet. But it's inevitable that this will happen sooner than later. So I would give an example, particularly for display technologies I'm talking about. There is a lot of composition work that happens in getting the right attributes, both from mechanical perspective, optical perspective, and the combinatorial work that needs to happen, that's huge. And we have used it to actually narrow it down to the compositions we should evaluate more closely. So it has happened, but it hasn't reached the stage there where it's completely formalized.
Right. Okay, so maybe there is a little bit of hype in that narrative.
No,
Okay.
no. But it's going to change. It is absolutely there. It's happening everywhere. Everywhere you turn, AI is being considered very, very seriously.
Well, I think given that we're fairly far along, I thought I would open it up early to questions from the audience. So, does anyone?
Just a quick question. You mentioned in the first part the new fiber that's more impervious to bending loss. Can you talk a little bit about the innovation that enables this? Materials, design?
So there is a core which carries the light, and there is a cladding. And light likes to travel in straight path. Bend it, couples light with the overclad mode, and it leaks, right? So back in this is from the clear curve days, this is 17, 18 years back when we first came with the invention. You actually provide a lower index region, right? And what that does is it traps the mode and stops it from leaking out. So that is the essence of the invention, a Cliff guide note how that works. But that's one part of the invention, you do that. You take these fibers, you can put a low index region, confine it, but all other optical properties of the fiber can change as well. And since these fibers have to be standards compliant, you have to work on other aspects of things such that you are getting the benefit of that and still be able to keep optical performance of all other things where the traditional legacy fibers have been. And so I said contour is a little bit of clear curve on steroids. That is more of even some of the properties we relaxed in developing clear curve, we have fixed, and so it's completely compatible with legacy fibers.
Got another one up here.
Thank you. With this technology, like almost any new innovations in telecommunications, it's obviously going to initially be more expensive. Is there a projection or timeline to when this technology will be similar in pricing and availability to the legacy technology?
So some of this, I may not answer this question directly because some of the information is proprietary. Okay, so I will dance around it a little bit. It is getting deployed right now. And until any of the products, any of the innovations, and other speakers who will come and talk to you, if there is not a value prop economically, it will not get traction. So I hope I answered the question that you had asked. So you have to be very sensitive about, unless it brings value to your customer in terms of attributes, and it is cost effective for them. It will not succeed.
Okay, thank you. I'll ask one more question then, since you kind of danced around that one. I see that a significant part of your professional career has been with Corning, but yet you are still distinguished as an individual inventor. What is the professional relationship you have with Corning in these innovations where you're still an employee, but you still get your individual recognition?
And I think that's best way to do is Corning provides, particularly in science and technology, for a scientist, I'm speaking for that, an environment that, your inventions are helping the corporation, but at the same time you are professionally and personally developing as well.
Okay, thank you.
Yeah. So, and some of the recognitions, they are testimony to that.
Okay, thank you.
Over here.
Hi,
Hi.
Great talk. You mentioned at the beginning of the talk the invention of the optical fibers about 12 years before there was need for it, and I think the same is true for Gorilla Glass. It was invented way before there was a need for it. What mindset in this company at Corning allows for the invention of these products before there's a need for it in the market?
Yeah, we do focus on the mega trends, and we try to anticipate what are the inventions that bring value. So that's there. But a lot of times, the invention is there, but the ecosystem is not there. Ecosystem is not there, you are at the wrong place, not at the right time. You have to be at the right time, at the wrong place. And so you have to anticipate not only what you will develop, but how the ecosystem will develop as well, right? We'll give you an example. And sometimes there is a serendipity part as well. We'll give you an example. The Gorilla Glass we talked about, that is on most of the iPhones, and the original invention was in 1961 that was meant for windshields for cars and didn't go anywhere. The incumbent technology was good enough. It didn't break. it was not considered. In 2006, when there was this transition happening, the iPod was about to come, and polymer screens were not as attractive to a glass screen, but it's brittle material. Glass is a brittle material. You had to get something which is much more resistant to breaking. That is where the invention from 1961 suddenly became important. So you anticipate it, and you hope, you keep an eye, not hope, you keep an eye on the ecosystem, how it is developing, such that when you are ready with the invention, the whole ecosystem is there for that product to have a value.
Turns out it's a lot harder to drop your windshield on the floor than it is to drop your iPhone on the floor. We've got one over here.
Do you see your life's work as a means or an end to a solution from this macro view, or do you view it as something else?
That's a deep question, and I don't know what. I haven't thought it from that perspective. I'm having fun. I was trained as a chemical engineer to look for particles, but over the last 25 years, I've learned to do how does light interact with materials. I've learned to do polymer science. I've learned to do glass science. I've learned to do solid mechanics. Till the time I'm learning, I'm happy with that part. So I haven't defined it in the way. So no big goal, you're just having fun.
So, can I ask one more question? Do you see all these things as kind of means to your end? And would your end be having fun?
No,
In that case?
Not quite. So the main thing is, one thing that probably all of you appreciate, the big inventions happened at the cross-section of interdisciplinary sciences. So at Corning, I do get to work with people with very diverse background, very diverse skill set, and I learn from them. And then I learn new areas because I'm working with them. So a lot of big inventions are right. They are not in a specific field. They are at the intersection of interdisciplinary science. There's material science, there is engineering, there is design work, all of that.
There was a remark Pushkar made to me earlier, is that basically everything he's doing now he learned since he got to Corning, not in preparation. So maybe there's a lesson for all of us here at Yale about training that you shouldn't necessarily expect to know everything that you're going to do in your future career just from what you learned here. We may have time for one more, and I'd love to hear what Juan has to ask.
Now, you mentioned that you have 300 inventions. That is, how on earth is it possible? Because I hear that Edison had 1,000 inventions, and he had a huge team under his orders. And he described every invention taking thousands of experiments. So question number one is, how can you do possibly that thing, that defeat at the Corning? And the second, what fraction of them really has brought any money or any funds to Corning?
It's how it happened, I have no idea. It happened along the way. So that's and frankly, in last 26 years, I've been an individual contributor. I have no people reporting to me. But I collaborate with a lot of great colleagues. So that is one. I've never had people reporting into me. And that was by choice. That was by choice. So, but I collaborate with very smart colleagues. I learn from them. I teach whatever I can. So, and talking about the impact, that number could be in billions.
But what fraction of these
So, percentage, I have to make a guess. I think it's on the order of 20%. 20% that have been commercialized. That has been commercialized. So when I said billions, it would be over the lifetime of the product multiplied multiple years. But it would be a 20% commercialized. 20% of products and processes and cost reduction things that have been commercialized or implemented in manufacturing. Something on that order.
Okay, well, thank you once again for coming, and thanks to all of you for coming here.
Thank you for hosting me.
Please stick around for the reception, and you can ask some more questions directly. We'd also like to thank SciCity for hosting us here today. This is always a great space to have these events. So stay tuned. We have more of these coming up later in the year, and we'll be sure to get the word out. Okay, thanks again.